Have you ever questioned the nature of your reality? Is everything you perceive with your senses real, or could it all be an illusion? This is the provocative query at the heart of the simulation hypothesis, a mind-bending concept that has intrigued philosophers and scientists alike. Imagine this: the scent of your morning coffee, the warmth of sunlight on your skin, even the rush of wind against your face, are all part of an intricate computer simulation. This isn't just science fiction, it's a legitimate philosophical argument first proposed back in 2003. The simulation hypothesis suggests that if we, as a civilization, ever reach a point where we can recreate the universe in a computer simulation, then it is highly probable that we are already living in one of these simulations. Now that's a thought to stir your morning brew. If we are indeed living in a simulation, what could be the implications of this possibility? The simulation hypothesis isn't just a wild idea. It's a philosophical argument that has been explored and debated by scientists and philosophers alike. Born out of a thought experiment published in 2003, this hypothesis suggests that we could all be living in an intricate simulation, much like a computer game. Imagine, if you will, that our advanced descendants have managed to simulate the universe using some kind of hyper-advanced computer. If they've done this not just once, but countless times, then statistically speaking, it's more likely that we're living in one of these simulations rather than the base reality itself. This hypothesis begs some thought-provoking questions. If we are indeed in a simulation, then everything we experience is just a model of something else, a mere reflection of a more profound reality. Our lives, our joys, our sorrows, even the universe itself might be nothing more than sophisticated data in an advanced computational system. It's a concept that blurs the boundaries between science, philosophy, and even spirituality. However, it's important to note that the simulation hypothesis, as captivating as it is not universally accepted. Critics argue that it's based on a number of assumptions that may not hold up. For instance, it assumes that future humans will have the capability to simulate entire universes, an assumption which we have no way of verifying. It also assumes that these future humans will choose to create such simulations, another assumption that we can't back up with any certainty. But despite these criticisms, the simulation hypothesis continues to be a topic of fascination. Some scientists even believe that certain physical phenomena could be signs that we're in a simulation. For example, quantum mechanics, with its bizarre and counterintuitive principles, could be interpreted as evidence of a simulated universe. The simulation hypothesis, while fascinating, remains a speculative idea. But there are some scientific theories that could lend some support to it. And as we continue to explore the nature of our universe, who knows what we might discover. One such theory that could support the simulation hypothesis is the Second Law of Infodynamics. This law, proposed by physicist Melvin Vopson and mathematician Serban Lepidatu, takes inspiration from a fundamental principle in physics, the Second Law of Thermodynamics. To understand the Second Law of Infodynamics, let's first revisit the Second Law of Thermodynamics. This law states that in any natural process, there's always a loss of energy, leading to an increase in disorder or entropy in the system. Imagine a cup of hot coffee sitting on your table. Over time, the coffee loses its heat to its surroundings, the energy disperses, and the system becomes more disordered. Now, let's translate this idea into the realm of information. Vopson and Lepidatu proposed that, similar to physical systems, information systems should also experience an increase in disorder over time. They coined the term information entropy for this disorder. However, what they found was that information entropy didn't behave as expected. Instead of increasing, information entropy either remained constant or even decreased over time. So what does this mean? Let's take an example. Consider a digital data storage system. Over time, instead of becoming more disordered, the system maintains its level of information entropy. In some cases, the system might even become more organized, decreasing its information entropy. This is contrary to what we would expect based on the Second Law of Thermodynamics. This revelation of the Second Law of Infodynamics has far-reaching implications. It suggests a fundamental difference between the behavior of physical and information systems. and this could potentially pave the way for a new understanding of our universe, possibly even supporting the idea that we could be living in a simulation. This law suggests that the disorder of information systems, or information entropy, could either remain the same or decrease over time. This unexpected behavior of information entropy might just be a clue that our reality is not as it seems. Stay tuned as we delve deeper into the implications of this law in the next segment. Physicists Melvin Vopson and Serban Lepidatu have used this law to explore various fields such as genetics, cosmology, and atomic physics. Their research has led to some intriguing discoveries that further illuminate the second law of infodynamics. Let's first take a look at genetics. In a fascinating study, Vopson analyzed RNA sequences of different variants of SARS-CoV-2. He found that as these variants underwent mutation, their information entropy actually decreased. This was a surprising result, as one might expect the process of mutation to increase disorder, or entropy. However, this finding aligns perfectly with the second law of infodynamics, which posits that information entropy ought to remain the same or even decrease over time. And what about atomic physics? Well, here too, the second law of infodynamics seems to hold true. Electrons within an atom, it turns out, arrange themselves in a way that minimizes information entropy. This suggests that even at the atomic level, there's a certain orderliness, a certain symmetry that fits neatly within the framework of the second law of infodynamics. But the implications of this law don't stop at the microscopic level, they extend all the way to the cosmos. Vopson's research suggests that for the universe to continue expanding, the increase in physical entropy must be counterbalanced by a decrease in information entropy. This is a profound insight that not only deepens our understanding of the universe, but also lends support to the simulation hypothesis. In all these examples, from the tiny world of RNA sequences to the vast expanse of the cosmos, the second law of infodynamics seems to be at play. It's as though there's a hidden hand guiding these systems towards a state of decreased information entropy. Their findings suggest that the second law of infodynamics could indeed support the simulation hypothesis. So, could we really be living in a sophisticated simulation? Well, the jury's still out on that one. But one thing's for sure. The second law of infodynamics is opening up new and exciting avenues for research, and who knows where they might lead us. So, what does all this mean for the simulation hypothesis? We've spent some time discussing the simulation hypothesis, the idea that our reality might be nothing more than a sophisticated computer program. We've also delved into the second law of infodynamics, a concept that provides a fresh perspective on how information behaves. This law, proposed by physicists Melvin Vopson and Serban Lepidatu, is a fascinating twist on the well-known second law of thermodynamics. Instead of energy systems increasing in disorder over time, as thermodynamics would suggest, Vopson and Lepidatu found that information systems either maintain or even decrease their level of disorder, their information entropy. This unexpected discovery led Vopson to suggest that the second law of infodynamics could provide scientific support for the simulation hypothesis. Let's unpack that idea a bit. If our world is indeed a simulation, then everything we experience is a model of something else, a digital interpretation of some real reality. In this context, the behavior of information as described by the second law of infodynamics makes a lot of sense. A computer simulation would aim for efficiency, and maintaining or decreasing information entropy is a highly efficient way of handling data. It's like tidying up your digital workspace as you go along, rather than letting chaos reign. Vopson and Lepidatu further tested their law in various fields like genetics, cosmology, and atomic physics. In each case, the law held up, adding further weight to their proposal. So while we're not saying we're definitely living in a computer simulation, these findings certainly make the idea more scientifically plausible. The second law of infodynamics could, in fact, be a key piece of the puzzle, providing a scientific basis for an idea that has, until now, been largely philosophical. Whether or not our reality is a sophisticated computer simulation remains a question, but the second law of infodynamics certainly adds another layer of intrigue to this fascinating debate.